The topic of this talk is about computing volume of a convex body in high-dimensional space, and we'll give an almost n-cube algorithm. This is based on a joint work with Aditi Letta, Intet Lee, and Santosh Vampala. So here is the problem. Suppose we have a convex set K with the membership oracle. That is, if you ask whether a point X is in K, the oracle answers yes or no. So then the problem is we want to estimate the volume of K within a small multiplicative error. So here are the previous results for the volume computation problem. Dyer, Fries, and Kynan gave the first polynomial algorithm in 1989. And afterwards, there were a series of improvements coming up with new techniques and its ingredients. Note here, the previous best result is n^4 by Lowas and Vampala. The last one only works in a special case when the convex set K is well-rounded. That means K contains the unit ball and it's almost contained in a ball of radius square root n. And in this special case, we'll got the complexity n-cube. We'll come back to this result later. And this is the main result from our paper, that we can compute the volume of any convex set in O star n to the power of 3 plus little o1 steps. And this is O star n cube if KL's conjecture holds. Here, O star means we omit the error parameter terms and the log poly terms. So it's almost an n-cube algorithm. Okay, here's the volume algorithm by Dyer, Fries, and Kynan. So we suppose K is sandwiched between a ball B and a ball RB. So we can think B as a unit ball, then RB is a ball of radius R. So this is the inner ball B. And then we define the sequence ball. So from B to RB with the radius 2 to the power of I over n. And then we let Ki to be the intersection of the ith ball and K. So this is K0 is just B and K1, K2. And then we can estimate the ratio of volume Ki over volume Ki minus 1 by taking random samples from Ki and then computing the ratio of points in Ki and Ki minus 1. So now we can see the volume of Ki. The volume of K is just, we can multiply all those ratios together and we'll get the volume of K. So we take this factor, we increase the radius of the ball in each iteration by a factor of 2 to the power of 1 over n. And we choose this factor because we want to get this claim that in each iteration, we want the volume of the intersect. So Ki increases by at most 2. This means we don't need too many samples to estimate the ratios. So if the ratio is too large, like in exponential, then we need to exponential number of samples to estimate the ratio. But now we only need n log r over epsilon square number of samples in each iteration. Then the total number of samples for 1 plus epsilon approximation is n log n. This is number of iterations times the number of samples in each iteration, n log n over epsilon square. And together we get almost n square number of samples. So the next question is, how can we get those samples? This is an interesting question on its own. That is the sampling problem. Same as the volume problem, we have a convex K, set K, with a membership oracle. And the output is a random point from the uniform distribution over K. And any convex body can be sampled in polytime. For example, we can use the ball walk. Ball walk is a common algorithm for sampling, and it's very simple. So we start from a point X in K, and then we pick a random Y from a small ball around X. So this is a ball centered at X with a ball with the radius of delta, and delta is the step size. So if the random point we pick from the ball is in K, we'll go to that point. Otherwise, we sample again. So we'll repeat this ball walk again and again until we get a uniform distribution over the whole convex body. And this ball walk works well if K has a good shape. But if the body looks like this, so there is a very small cut in the body, we may get trapped on one side, and it's hard to get across this cut. We can measure this property of the set K by a constant called KLS constant. So it's measure the property that whether it has a small cut with large volume on both sides. And it is defined as the psi K equals to the supremum over all subset S in K. And so this S divides K into two parts, S and K minus S. And we take the smaller one, the volume of smaller one, and divide it by the volume of the cut. So if psi K is large, we may have the case that there's a small cut and it divided into two parts and both has large volumes. And if it is small, then we can have this result by Konolovas and Semenovic. So the mixing rate of the ball walk in K from a warm start is n squared psi K squared. So this shows that the complexity of ball walk is directly controlled by this psi KLS constant. Note that this KLS constant is not a fine invariant. So for example, this is a convex body K, and if we stretch it in some direction, and we can see this cut, the volume of this cut stays the same, but the volume of the in this part and also in this part increases with the length. So psi K can be arbitrarily small in this case. But we can always normalize K so that the covariance of K is identity. And in that case, we say K is isotropic if K has a mean 0 and the covariance is identity. And KLS also has a conjecture that for any isotropic and convex K, KLS constant, psi K is a constant. Here are some results approaching KLS conjecture. Suppose A is the covariance matrix of K, and lambda I are the eigenvalues of A. Lambda 1 is the largest one. So this is there's a column gives the result about the psi K bounded by a function of eigenvalues of A. So even if it's not isotropic, we get some results about the eigenvalues of A and psi K. And KLS conjecture says that psi K is at most C times square root lambda 1 A. And this gives the mixing time of ball walk in isotropic position n cube, n square. And Cannon-Lovász and Samanovic proves actually psi k is bounded by c times square root sum of lambda IA. So this is just a trace of A. This sum is just trace A. So it's constant times square root trace A. And this gives a missing time of n cube. And later this was improved to 1/4. And then recently, Chen proved that psi k is actually bounded by a sub-polynomial on n times square root lambda 1a. So you can see this is very close to KLS conjecture up to a sub-polynomial on n. And this results gives a mixing time of n to the power of 2 plus little o1. Okay, and actually, this is the first result of the KLS conjecture. Already gives an algorithm with complexity n cube for well-rounded body. So remember, well-rounded body means that it is almost covered by a ball of radius square root n. And then if we use these results, we know that the sampling time for each, the sample complexity for each sample is n cube. And then we times with the number of samples we need, we've got the complexity to be n to 5 together. And then how can we improve that result? So here is an improvement in a different line. We have a better result if we assume K is well-rounded. So remember that K is well-rounded if it contains a unit ball, and is mostly contained in a ball of radius square root n. Cousins and Rampala gave a volume algorithm with complexity n cube for well-rounded convex body K. So with the new technique, Gaussian cooling. So this result shows if there is a fast algorithm to make general convex set to be well-rounded, we'll have a fast volume algorithm to combine the fast rounding algorithm with this fast volume algorithm. And this is the current rounding algorithm by Lovász and Rampala. We start with a ball inside K, and then use all the n samples to estimate the covariance of K intersect B. So suppose this is a B and this is K intersect B, and we'll try to make this convex body nearly isotropic. So we'll transform K by the covariance of these parts to make it nearly isotropic. And then we double the radius of B. And again, to sample from this larger body and to make this larger body nearly isotropic. And we repeat this until we get a large ball enough to cover the whole body. And we can prove that if K intersect B is isotropic, then K intersect 2B is well-rounded. So in each iteration, we start from a well-rounded body, K intersect B, and we'll sample all the n samples from this well-rounded body. And as we mentioned before, this takes all the n cube steps for each sample. So we get the complexity for this algorithm. We have log n iterations and n samples in each iteration, and n cube steps for each sample. And together we get almost n to the 4th complexity. So our main result is to improve the rounding algorithm with a faster complexity. So we show that any convex body can be brought into near isotropic position into its O n3ψ2 membership queries. This, combining with the Gaussian cooling algorithm, implies that the volume of a convex body can be estimated in n3ψ2 membership queries. And this ψ2 is the KLS constant. And so with the current bonds, we have the n to the power of 3 plus little o1 steps. And if KLS conjecture holds, we'll have n cube steps. Now I'll state our algorithm. So first, this is the LV rounding algorithm from before. We'll use the same outer loop as the LV rounding algorithm. So we increase the radius of the ball by 2 in each iteration. And in this inner loop, we'll transform K to make K intersect B nearly isotropic. And then we'll go into this inner loop. This is the most important part. So we want to make the well-rounded body isotropic. Okay, this is the algorithm. And we start with the K convex body K, and we assume K is well-rounded. We first set R to be 1, and then draw sample. We draw R square samples to estimate the covariance of K. So this R is the inner ball of the K. We'll always maintain a ball of radius R in K. And then that V be the subspace with variances at least n. So like in this picture, this is this rise eclipse is the K, and like V is the subspace in this direction. So it has large eigenvalues. And then we scale up along all directions that's orthogonal to V by a factor of 2. So we scale up these directions with small variances, and we got this blue convex body. And then we increase the radius R by a factor of 2 times 1 minus 1 log n. And we repeat until K converges to isotropic. So the intuition of this algorithm is that we keep scaling up the small variances so that at the end, all eigenvalues converge to n. And there are several important things to prove. The first one is in each iterations, we want to prove that a number of R square samples suffice. This means at first we only need few samples when K is far from isotropic. So we can see at first R is small, like it's just from a constant. And as the inner radius R increases, we need more samples. And at the end of the algorithm, R square will increases to n. So at last we'll need like n samples. And the second is the sampling time for each sample in iteration depends on R. So it's a n square sin square over R square sampling time. So this time decreases when K is closer and closer to isotropic. So when R is larger, that means the inner ball is close to like a ball of radius square root R. And we also know that the body is well-rounded. So it's also covered by a ball that's of radius square root R. So it's so K goes to close to isotropic. And then we, in that case, the sampling time will be smaller because it's easier to sample isotropic body. So these two results together show that in each iteration, the complexity keeps the same because when we multiply them together, r squared cancels out. And lastly, we want to prove that whenever we increase r, so we increase r by a fact 2 times y minus 1 over log n, and then we maintain the fact that K contains the ball of radius r. So these three facts gave the correctness of the algorithm, and the total complexity of this algorithm is, so we have the number of iterations log n times the number of samples in each iteration r squared, and the steps for each sample n squared is n squared over r squared, and together we get almost n3ψ2 steps. Okay, so this is the end of my talk. Thanks for listening.